Okay, I'll deal with that. All right, so today we have ourselves here a MacBook Pro 13. Let's take that step back. Hold on. And edit. All right, so today we have ourselves a MacBook Air 13-inch. This one's a A2000165. This one came in here for not booting. So initially I opened up this MacBook in front of the customer and noticed that there was a little bit of corrosion on the SPI JTAG terminal. So I'm thinking that's one of the reasons why this isn't turning on, but now we're also not getting a green light on our MagSafe. So that tells me that something's wrong with our SYS ONEWIRE circuit. I've gone ahead and removed the JTAG just to eliminate that being an issue. Still not turning on, so we may have had some damage done to our SPI ROM or BIOS. But let's go ahead and just start from the basics. So I'm going to plug in our DC power supply and start troubleshooting what's going on with the ONEWIRE circuit. Go from there. I'm going to plug in my power supply and let's see what we start drawing. We don't have a light, and I'm pretty much getting nothing. I'm getting 0.013. So that sounds like there's an early short or something stopping really early on in the computer to where it's not getting through the rest of it. So let's look at our schematics here and see what could potentially be our issue. So our power is going to come through. Let's take a look at our PP3V42_G3 hot power supply and see if all that looks normal. And our SPI ROM is right here, the J6100, and it's very possible something might be messed up around this area. So let's check and see if this is even getting turned on in our pin 6 on U7090. So we put this underneath our microscope. This is going to be our U7090. Oh, that's not what we need. Okay, there we go. And pin 6 is going to be on the bottom right hand side of our orientation. Take my multimeter and put it into voltage. And let's see if we're getting any power. All right, we're getting 18.2, so we are getting power to our chip. Let's take a look back and see what the rating is supposed to be. Yeah, 18.5, so we are getting voltage going into our U7090. This is going to be what creates PP3V42. So is it putting out power? Let's check to see if we even have our PP3V42. If it's present, then we're going to check out our power rails after that. And the board just flipped over on this side. Let's flip it back over to the orientation we're in. So that's going to be this giant capacitor or pin 2 on U7090. So with our multimeter, let's probe that area and see what we have. Pin 2. We're getting exactly 3V42. So now that we are getting power directly to our PP3V42, then we'll have to check what else is going on. So PP3V42 is going to have to talk to our SMC, and our SMC then sends a signal back to our MagSafe. Oh man, I forgot the name of the rail, but let's see if we can take a look at it. Take a step back. Let's take a look at what the ONEWIRE circuit looks like on an older MacBook Pro unibody. And I was actually looking at one earlier today, the A2002915. This is going to be a 15-inch 2011 MacBook Pro. But on the schematics here, it actually shows where the SYS ONEWIRE is located. So, just looking through the table of contents here, I believe it was still on here. I don't think they removed it. at the time, and I know it's right in my face. Let's do a search. So that's called SYS ONEWIRE. I believe it's spelled like that. It's not spelled like that. So SYS ONEWIRE. Is it one wire, one word? It is. All right. So on our schematic, it does actually show us what we're looking at. So on our 15-inch MacBook Pro, we have our MagSafe 1, which plugs into the board right here at J6900. J6900 sends 18.5 volts through PP8 18 V5 DC in fuse. It goes through a fuse, and then that fuse is going to go to PPDC in G3 hot, and if we follow that, that is going to go to our PP3V42 regulator. Here we are. So right here, this is going to be pretty much the same chip we're looking at on our MacBook Air. We're just referencing an old schematic here. And we can see PPDCN G3 hot goes through this diode, and this diode is responsible for taking power either directly from PP bus, which is going to be generated from the battery, or from PPDCN G3 hot, which is going to be generated from our MagSafe. And in this case, we only have our MagSafe plugged in, so it goes through this diode, and 18.5 volts goes through on this one, pin 7, then goes through our enable on pin 4, and then out is going to be PP3V42. So we do have that on our J6900. So let's go back. So SYS ONEWIRE. And from there, we get PP3V42, which comes to this logic gate. And this logic gate, how it works is if both A and B are present on this logic gate U6901, then Y will be the result. So as long as we have SMC BCACOK go to the logic gate, then it will send PP3V42 from 5, it's going to come out of Y, pin 4 becomes SMC BCACOK VCC, and that's what powers this chip here, U6900. And U6900 then sends a signal to adapter sense, and adapter sense is then what turns on the MagSafe charger. So we have to apply the same logic to our MacBook Air. And what I'm going to do just to make sure I can reference this is I'm going to just open up another Flex board view. And let's go back to our MacBook Air. So here we are. Now we've already verified that PP3V42 is present. So now let's check out to see if we have SMC BCACOK. Let's do a search for that. So that is SMC_BC_ACOK. Where are you located? It looks like it is generated from U7100. U7100 is going to be our battery charger, or our ISL, our inrush limiter, which then sends the signal to our SMC. So here is U7100, and we have our PP3V42 G3 hot, comes to pin 12 VHST. I'm not sure what that is off the top of my head, but here's SMC BCACOK. So that comes from pin 14 on our MacBook Air. Let's make sure that is present. So this is our battery inrush limiter. This is also what creates PP bus. So this is our inrush limiter. And we can see that we got PP3V42 underscore G3 hots going into U7100. But while we're here, let's just go ahead and check and see that SMC BCACOK is present. I'll turn on our power supply. And so that was pin 14, which is going to be that top left pin. And we're getting 3.3, so that is present. And we are getting our SMC BCACOK, which is 3.3 volts, which means that U7100 is turning on. So, let's reference our other schematic here from the MacBook Pro. So SMC BCACOK is then going to go through a logic gate right here, which then sends SMC BCACOK VCC to U6900. Do we have anything similar to that on our MacBook Air? Let's follow SMC BCACOK and see where it goes. Okay, and we know that that goes to our SMC. And then it goes through a resistor. It's going to be your J9500, which is going to be the MagSafe port on this MacBook. Okay, so we know that it's sending the signal to our SMC. We need to find out if our SMC is even turning on. SMC on off L. Let's see where this takes us. That's just going to be our debugging, but this is what I want to look at here is U5110. So this is going to be our reset button that actually sends a signal. So we want to make sure that SMC reset L is present. And let's see, is that anywhere near our JTAG connector? It is. So U6100 is going to be our JTAG connector. And if for any reason pin 12 is grounded, then it's going to be holding the reset button, preventing the SMC from actually powering on. And this is where all of our corrosion was. Let's revisit that and measure to see if we are getting any type of signal. We should be getting something like 3.3 volts. And we're not. So this is going to be where our issue is located. So either this is grounded or our signal, the U5110, which sends the SMC reset, was damaged in the process from the corrosion here. So I'm going to remove my power supply and put my multimeter into continuity mode and see if there's a beep. Alright, so there's no beep, so there's no immediate ground, short to ground, on our SMC reset. This is good. This tells us that there is an issue around our U5110. I'm going to get one of these cameras right. Okay, here we go. So SMC reset L is missing. This is going to be why we're not getting a signal on our MagSafe charger, because our green light, our SMC is not turning on, so it's not sending a signal back to turn on the adapter sense signal, which turns on the green light on the MagSafe 2. So now we got to explore this chip and find out well, let's give it a visual inspection, and then we'll also check and see, is it even being told to turn on? So U5110 is going to be just right above our Wi-Fi connection. Still working on the cameras. I'm working on a MacBook here. So what do you expect? So you are U5100. You don't look necessarily gross. Let's look back at our schematic here. So U5100 is going to be powered by PP3V42_G3 hot, and that goes into pin 1, which if we look is going to be our top left. Let's see if we have any voltage going through. So we'll hook back up our power supply. And with it connected, we'll take our multimeter and we're just going to tap the top left. Are you being told to turn on? You are. So we are getting 3.42 volts on U5100 or U5110. U5110. I'm not good at numbers like other technicians are, but that's just one of my many faults. So, excuse me. So pin 1 is getting power, and we know that PP3V42_G3 hot is present, so we should have it present right here, which goes through a resistor, a very, very low resistor. It actually says 0 resistance, and then goes through, becomes PP3V42_G3 hot _ SMC_SPVSR. What is that? Supervisor? What does that stand for? But we should be getting also a voltage of 3.42. Let's see if we are getting that. So that is on pin 3. So if we look back over here on our board view, that's going to be, there's a little test point right here. So let's probe that test point. We're getting power there. So that's not our issue. And now let's check and see if U5100 is acting as a pull-up resistor, if it actually has 100 kilo ohm resistance. So for measuring resistance, what we have to do is turn off our power supply. We don't want to measure a live system while it still has power on it. And then we're going to put our multimeter into continuity mode, or I'm sorry, into resistance. Oh, where is, excuse me. So where is U5100? I didn't click on that. Oh, awesome. All right, so it's next to our SMC on the other side. So I got to flip the board over again. Yeah, it's just a lot of hair. So U51, or I'm sorry, I'm just spouting numbers now. R5100 is going to be this resistor right here. So we should be having about 100 kilo ohms. And with my multimeter, I'm getting a resistance of 53. This is more likely our issue here. So let's go ahead and replace this and see if we can get the computer to turn on. And for that, we need our donor board, which we conveniently have plenty of donor boards for this model down here. So here's a donor board, and just to make sure that that is indeed the right resistance, I'm going to measure the impedance on R5100 on this board. We should be getting about 100 kilo ohms. That's exactly what I'm getting. Awesome. So this hopefully is our only issue. The board's not liquid damage, but there is just that tiny little bit of corrosion that was on J6100, which is the SPI JTAG terminal that doesn't need to be there post-production. It should be removed before it gets shipped out of the factory. But the customer did say that they did get a humidifier, so it's possible that she had just enough humidity from the humidifier to damage or build up corrosion, or build up moisture, which then went into our J6100. Which would be really, really disappointing if a common house humidifier is what can kill these computers, but that's what we deal with here. So this is our patient board, the board that's being worked on. Let's put some flux on it. And I'll take our micro tweezers and just touch both ends and pull it off. Set that to the side. Let's get our donor board. Just like with the patient board, we're going to use some flux. And this is where I like to act fast. So I'll grab the resistor, and then I will grab the other board while I'm still holding the resistor. And just put it on.
Okay, so you already opened it.
And there is our resistor. So let's see if that fixed it. Set the donor board to the side. And let's turn on our power supply and see if we get a green light. Still nothing. And we're still pulling the exact same amount of current. So that wasn't our issue. So now that we've replaced that, but it's still not turning on, let's first find out if this is getting all the proper signals to turn on. So looking at U5100, or U5110, we saw that our pull-up resistor right here of R5100 was not present. So it wasn't sending out our SMC reset L. Let's check and see if our SMC on-off low is present. Okay, and we're back. So SMC on-off low, it's going to be pin 7 on our U5110. I thought we were so close. I got just a little overzealous there. Okay, sorry, I had to assist a customer there for a second. So we were trying to figure out our SMC on-off low. So basically this is our switch. This is what actually turns on. So whenever this drops low, it is the equivalent of pressing the power button. And there is power there, so we don't need to drop that low. It should be turning on by itself, but it's not yet. And SMC LOC reset low, which is going to be on pin 6. .4. So that seems fine too. Now let's look and see what is going on with pin 8, which is going to be our reference coming out that goes to the SMC. Alright, sorry about that, just had to help another customer there for a second. So where we left off is on SMC reset L was not present, and because of that, our SMC is constantly being held down in the reset position. The best way, Jessa Jones actually did a very good job describing this. So just like on the old video game consoles, like a Sega Genesis or an Atari, there was a reset button, and if you held the reset button down, the console would never turn on. Well, SMC reset is held down when the signal is low. So it's a very low voltage or no voltage at all. So we want some voltage here, which will then send a signal to our SMC to turn on. But if there's no signal, then this is held down. This is L. It's a reset button. It's holding down the SMC. It's preventing it from turning on. So what we did is we saw that R5100, which is a pull-up resistor, was missing a... Is it a pull-up resistor? It's a resistor nonetheless, and it's supposed to have a resistance of 100 kiloohms. We weren't getting that. We were getting about 50-something kiloohms, so we went ahead and we replaced that. So after doing that, it's still not turning on, but let's see if SMC reset L is present. So that's going to be pin 5 on a U5110, which is our bottom right. And switch back over to our overhead camera and see if that is present. Take our multimeter, put it into voltage, and touch the bottom. And we're still not getting anything here. So if it's not turning on and all the right resources are here, did we check to see if PP3V3S5 AV ref SMC is present? That was going to be pin 8. SMC reset L is not present, and PP3V3 underscore S5 AV ref SMC, we're going to check and see if that's present. So that's on pin 8 of our U5110. And we are getting 3.3. So this is present. So is this shorted? Let's turn off our power supply. I'm going to put this into resistance instead. Measure what the resistance to ground is. And we're in the mega ohms, so that's not the issue, but we're not getting a signal coming out. Is it possible that our U5110 is bad? Is there something that I'm missing here? Before we start blaming the chip here, let's check and see on pin 1 of our R5100 that we replaced. Are we even getting voltage over there? Do we have power coming on the right side? We do. We do have 3.4. What about over here? So power is going there. Let's check our resistance, make sure we didn't do anything stupid. So if we touch our probes together, yeah, we're getting a resistance of 0. As far as resistance go here, I'm now starting to get a resistance. About 50 again. But it's going up to 80. It's fluctuating, which leads me to believe... What does it lead me to believe? It leads me to believe the common denominator between the resistor here, both sides are going to go to our U5110. So, oh yeah, it's jumping all over the place. It's very possible our issue is with U5110. Just to make sure, I held onto our old resistor. I didn't actually throw it away. And I was getting a strange reading. Come on. What reading do you give us? Okay, so our resistor that I thought was bad is actually giving us the proper reading of 100 ohms. So I'm going to say with that, our U5110 is bad and it is messing with our resistance we have here. And just to show you why I think that is on U5110, we're checking R5100. And R5100 on one side, which is pin 2, is going to be our reset. And the other side is going to be going into our PP3V42, then it goes through this other resistor right here. Yeah, I haven't even checked this resistor. But what I was thinking is that since this goes through this resistor and then back to pin 3, and then this on this side goes to pin 5, maybe our variable here is going to be our U5100. But now that I've said it, let me look at our R5127, which is going to be directly next to our U5110. Poor resistor. I'm sorry I blamed you. We're going to set you aside. We'll put you back on your original, or on the donor board. So if we ever need it in the future, we have that. It's 7 o'clock, so it's officially closing time. Let me see if I can finish this up before we get out of here today. So this is going to be our R5127. Let's put it into resistance. We should be having a resistance of 0. And that's exactly what we get. You're fine. I'm going to replace you. You are potentially our issue here. For that, we need to remove our Wi-Fi, our airport card that's still here. If this works, then that means that the corrosion on our SPI JTAG terminal was enough to send a short back up to our SMC reset component and kill it. Okay, so I've misplaced my tweezers, so I'm just going to use these tweezers I got from Mobile Centrics. They're Cassie tweezers. They're larger than my Hako tweezers, but they will work for what we're trying to do. I really need to get my thought process organized on logic boards. First step should always be checking our power rails. This one I just kind of dived into it thinking that, oh, our issue is going to be with our PP3V42, but turns out it's going to be closer to a different component. So the interesting thing about this logic board too is the customer had gone to an AASP who then quoted her $800 for a board replacement, which I find to be fairly high for this board because I've heard Apple has quoted much lower than that. I'm not sure if that was their independent pricing or if that was their pricing from Apple, because if so, then that means Apple has raised their prices on board replacements for these MacBook Airs. In this MacBook Air in particular, the 820-00165, it's either going to be a 13-inch 2015 or a 13-inch 2017. Now we're going to grab the same component from our donor board here. Just $800 for a 2015 or 2017 logic board. I find that to be just overly outrageous because I've heard board replacements are typically around 90% the price of the computer, but in this case, it is almost 100% the price of the computer. because let's say this is a 2015. Well, you can't buy 2015s anymore, but if you did, I'd say the computer would probably still be around $500 to $600. I mean, this one doesn't have a terabyte solid state. Even then, that's a modular part. That shouldn't affect the logic board price. But even if it was 2017, right before the new iteration of the new MacBooks, I mean, the highest one was right at $1,000. So they would be right at 80%, and if they did $800 for a board replacement. But I don't think that's what Apple's charging. I think that's what this independent, or I shouldn't even say independent, because they're an ASP. Let's wick up the old solder and put some new low melt solder. My wick actually has too much solder on it from the last wicking. And my pliers are gone. My, not pliers, but my wire cutters. Found them. I was quick to blame someone on that one. That one was me. So now that we have our pads all nice and tinned up with our low melt solder, that was my solder that just fell. Let's go ahead and put the replacement SMC reset IC in place. So we have a whole bunch of solder sticking out. We're going to fix that by going with our micro knife. It is an attachment to the micro pencil. It makes touching up these small points very, very simple. So out of curiosity, before we do anything else, I'm going to touch our R5100 and check and see if we're getting any inconsistency with our readings. So, because before we were getting about a solid 100 on our donor board, but on our normal board, we were getting ratings jumping all over the place, and we are getting a solid 100. So, let's see if that fixed it. Let there be light. We have a green light, we have a fan spin. Excellent. That's a successful board repair. We're going to, of course, give this one a bath and then do a quality control test. But this one was really fun to figure out. So this one came in from an AASP, or the customer declined getting it repaired at an AASP, and then came here instead for us to take a look at it. So we opened it up in front of her and couldn't find any signs of liquid damage immediately until we put it under our microscope and saw that our SPI connection, the J6100, had a little bit of corrosion on it. Uh-oh, did our team viewer just disconnect? It is. Bear with me for one more second. How much have you drank? Have you finished your Gatorade yet? Sammy, that whole bottle is only half of your intake of daily recommended water. Okay, sorry, I had to fix our connecting to our computer here. So I don't have a capture card, and I'm just using a MacBook Pro. So what I'm having to do is just team view onto my main schematic computer here, just to double check, or just to show you what I'm seeing. So I'm not actually rendering this on my my MacBook. This is my lovely wife who's feeling sick after donating blood yesterday or 2 days ago. But to get back onto here, so just to show you exactly what we noticed. What we discovered is J6100 had some corrosion. Well, we went ahead and we removed J6100, and we made sure that we were still getting our shorted line, which was PP3V42_G3 hot. Well, we know that needs to be present in order to send a signal to our SMC reset, which is U5110. And U5110 is then going to send out SMC reset L, which then goes directly to our SMC, which then talks back to the adapter sense on our MacBook Air. Well, we did see that U5110 was getting all the proper power. It was getting all the proper enable lines, but it was not actually turning on. So we looked at R5100. We thought R5100 was the issue because when we measured it with our multimeter, we were getting 100, or we were only getting 50 kiloohms instead of 100 kiloohms. Well, we went ahead and we replaced it with our known good R5100 off of our donor board, and we were still getting a resistance of 50 kiloohms. So the only other thing we're measuring when we touch pin 1 and pin 2 on our multimeter on R5100 is going to be, if we go back through here, it's going to be pin 3, which is our VIN on U5110, and our pin 5. And so being that all of our power was present, but we weren't actually being powered on, and we were measuring the resistance between pin 3 and pin 5 rather than pin 1 and pin 2 on R5100. We were measuring pin 3 and pin 5 on U5110. That was enough evidence to know that the corrosion on J6100 was enough to send some power to directly kill our U5110, which never sends our SMC reset L, which never turns on our SMC, which never sends a signal back to our adapter sense, which then turns back on the light to allow the computer to start charging, or just let alone our one-wire circuit. So that was the quick tail end to why this MacBook wasn't working. We went ahead and we've replaced U5110. The MacBook's working. We're just going to give it an ultrasonic cleaning, then do a quality control test, and send this out the door with the customer. Ooh. Sorry, I normally don't talk that fast, but I was trying to sum that up because I basically had to do that twice just now. Anyways, we have a fixed board, and that's it for now. If you enjoy these videos, please let me know in the comments below, and I will see you in the next one. Thank you.